Hello guys, welcome back to our new tutorial. In this series, we are going to learn the Ansys CFX, and in this 2-day video, we are going to set up a multi-phase flow simulation in Ansys CFX. Also, we will see how to set up the rotational domain in the Ansys CFX. So today we are going to learn a lots of things. So let's start. First of all, let's overview the problem. So our objective is to simulate the mixing of air and water in a vessel, and also we want to calculate the air distribution, the air mass fraction in the tank, the torque calculation of the impeller. And if we talk about the system geometry, our system contains tank, baffles, a rotating impeller, and a vertical shaft that rotates the impeller. If we talk about the flow conditions, the air is being injected through a 2.48 centimeter pipe at a speed of 5 meters per second. And if we talk about the impeller speed, the impeller is rotating at 84 rpm in the counterclockwise direction. Also, we take the assumption that water and air has a temperature of 25 degrees centigrade, and also the air is incompressible, and the diameter of the air is 3 mm. So let's start. First of all, we have to drop down the CFX. Now double click on the setup. Click on file, import mesh, go to the files where the I will provide the source files in the description, so you can download and practice. So we have two types of mesh. One is .geo format and one is .gtm format. First of all, let me choose the GTM format from here. Open. So you can see the impeller domain here. Now we have to import the tank domain. So change the type to .geo. So here is the tank domain. So if you see these two domains, these are not perfectly intersecting with each other. So you can see there is a lot of intersection between the fluid domains. I want to say that the surface of the tank and impeller domain are not intersecting with each other, but there is an intersection of volume. So to fix it, first of all, delete the default domain. Now come to the impeller meshing, right click, transform mesh, select the rotation, change the rotation to translation. Now we have to provide the values. I have written it here. Okay, we want to move our mesh in x direction. Click apply. So now you can see both of the mesh surfaces are perfectly intersecting with each other. So if you are working with the meshes that have more than one input mesh, so you can so if there is a problem with the intersection, you can use the transformation tool to align the meshes with each other. So the meshes are being fixed. So now we have to create a fluid domain. Impeller. Okay. I have selected the main domain, that is impeller. It is fluid domain. Also delete the default material, and let's come to the setting. We want to add two materials, air and water, and the water is treated as dispersed fluid, and the diameter of the water is 3 mm. So let's create the air. Okay, it is not a continuous fluid, it is a dispersed fluid, and the mean diameter is 3 mm. Okay, now create a new fluid, water. Change the material to water. It is a continuous fluid. Also add the gravity effect. So gravity is acting in the negative x direction. Also the buoyancy density is 997. Okay. Also the domain is a rotating domain, and the angular velocity is 84, and the axis is x-axis. Change the axis to x. Now come to the fluid models. We are not using any free surface model in this simulation. Also there is no heat transfer. If we talk about the other setting, I am not going to use the isothermal, but you can enable it if you want to study the heat transfer. But there is no heat transfer right now in the simulation. Yeah, there is some heating due to viscous layers of the water and air, because the water is moving in a tank, so there will be some heat generation due to viscosity. But I am not going to study it, so I have opt that model. Also, if we talk about the turbulence, so it should be fluid dependent. Now come to the fluid specific models. And what we have to provide it here, water is k epsilon. The turbulence model for the water is k epsilon, and for air it is fine. Okay, if we come to fluid pair models, we have to provide the surface tension coefficient, which is 0.073 Newton per meter. Also, if we talk about the other mathematical models, we have to choose the drag option as grace, and for turbulent dispersion force I am using phase averaged. So that is not phase average, I have mistakenly written it. It is favor averaged, and it's also we have to set the drag force to grace. Okay, click on OK. So one of the domain is created. Now we have to follow the same procedure for the tank domain. Click on this. Okay, we have to use okay, we have to use the assembly too, so it's fine. again the same, air, water. The point force is active, but it's stationary domain. There is no mesh deformation. All of the setting is similar, just we have to make it stationary. Same grace model, particle model, same surface tension. All of the models are same, just we have to change the domain to stationary. Click on OK. Okay, now come to the boundary conditions. Let's create the inlet boundary. Choose the location. Inlet inlet dip tube, because the tube is dipped in the water. Click on OK. Okay, we have to provide the normal speed. First select fluid dependent. Now come to the fluid values. The air is entering at 5 meters per second with the volume fraction of 1, and the velocity of water is obviously 0, and the volume fraction is also 0. Okay, click on OK. Now again create a new boundary condition outlet, or we can say it degas wall. So you have to select an outlet, location, there will be a name of degas. Wall liquid surface. Okay, so come to the boundary details and apply the condition of degassing. So what is the degassing condition? The degassing conditions mean there will be no liquid will go out of this domain, but the only condition is that if the outgoing fluid is gas, it will transfer from the outlet. But if the liquid is in if the fluid is in liquid state, it cannot go from the outlet. So so you can say there is a if condition. The fluid only pass if it is in gas state. So that is that is the degassing condition. So let's create the wall conditions, because we have to provide two types of walls. One is slip wall and one is non slip wall. So let's see what I am saying. Okay, first of all we have to create a wall baffles. Click OK. Okay, it's fluid dependent. Air have free slip wall condition, but the water has no slip wall condition. Click on OK. Similarly, create a new boundary. Choose the name wall shaft. Click OK. Okay, now we have to choose these two walls. Click on OK. Click on boundary condition. It is fluid dependent. Also the fluid values. The air has free slip wall. Also click on OK. So here we come. You can see for air there is no extra options, but if I click on water, there is the option of wall velocity. I have to select the rotating wall, and the global axis is x, and the rotation is 84 rpm. Click on OK. Okay, so now in the impeller domain we have to create this wall. Click on wall and hub and shaft. Okay, the values for the air is free slip wall. Click on OK. Now again we have to change the tank default conditions. Similarly, free slip wall. Okay, all of the boundary conditions are defined. Now come to the interfaces. We have to create some of the domain interfaces. Actually there is a lot, like we have to create 5 interfaces. So first of all, blade thin surface, paste the name. Okay, this from fluid to fluid, impeller to impeller. So at the first side, the region 1 is blade. Click on OK, and it is automatic selected the other 2 regions. Okay, and if we talk about the side dependency, we have to select a fluid dependent model. There should be some mesh connection material is fine. Okay, it is side dependent. Just we have to select this and click on OK. Now create a new interface. Now we have to create the interface for periodic boundary condition. Like you can see, we do not have created the complete circular tank, but we have only created a small region of the tank. So for that we have to create the circular periodicity. So click OK. So it is impeller to impeller. Select the periodic 1, and from here select the periodic 2. Okay, about the general connection, there is rotational periodicity about the global axis x. So just now the periodic boundary condition is created. Click on OK. Again create a new interface, tank periodic interface. Now we have to select the tank domain. From here also we have to select the tank domain. So now we have to select these 2 names. So first of all, here is tank P1 and here is tank periodic 2. So general connection is rotational periodicity. The axis of rotation is x. Click on OK. So now we have to create some of the other interfaces that are frozen. First of all, the top. It is between impeller and tank. So select impeller and tank. Okay. From the impeller side we have to select the top, and from the tank side we have to select the bulk body tank top. Click OK. General connection and frozen router. Okay, click on OK. Again click interface bottom. The first side is impeller, the other side is tank. So click on bottom. OK. Now click on tank bulk body bottom, this wall, and click on OK. General connection and frozen router. Click OK. Now create the final interface, that is outer. It's impeller and the second side is tank. Select the outer boundary, and from the tank select the bulk body tank outer. Click on OK. Change the frame setting to frozen router. Click on OK. So all of the boundary conditions are defined, the interfaces are too defined. So now come to the solver. First of all, edit the solver setting. Change the iteration to 200, minimum iteration to 20. I am using the default convergence criteria. And time scale factor, instead of auto time scale factor, I am going to use the physical time scale factor, because there are lots of turbulence in the tank. So I am just using 1 second to have the converged solution. If you use the auto time scale, so might be possible in the solution you will get the convergence error, because it is not easy to identify the turbulence in the rotary machinery. So now what other we have to change? The coupled volume fraction, sorry, we have to select the volume fraction coupling. Okay, and the other thing, okay, it is created. Okay, click on OK. Now one more thing we have to create is the monitor. So first of all we have to create these equation. Copy the tank hold up, insert expression, click on OK, and we have to, I am just copy and pasting. Basically we are taking the volume average of the tank and the parameter is air volume fraction. Click on apply. Now create a new expression. And I am copying this expression from here. Click on apply. Now again create a last expression, total air hold up. Okay, and copy this equation. So okay, here is total air hold up. So now again come to the output control monitor, create a new monitor, that is air hold up. Okay, so from the option click on expression. Okay, this thing we want to study, click on OK. Okay, there is a problem in the expression if you see.